Hi guys, welcome back to Data Every Day. Today we're looking at a data set of LendingClub loan data. So we can't actually see the preview here, but we're going to try to be predicting the class, or rather the grade of a loan, which is just a measure of how safe of a loan it is, based on a series of attributes. So I've already loaded in the data because it's a pretty big file, and notice that I've used let me just start, take a step back. We have the task for today, which is given data about accepted LendingClub loans. Let's try to classify the grade of a particular loan. And we'll be using TensorFlow artificial neural network to make our predictions. For the imports, I'm just using, I actually ended up not using Seaborn in this, so I'm going to keep it out. But we have NumPy, Pandas, Matplotlib, .pyplot, for just basic stuff, and then for pre-processing we have label encoder, standard scaler, and the train test split function from sklearn. And for our actual model we'll be using TensorFlow, like I said. So I've loaded in the data with the Pandas Read Csv function, and I've specified compression equals gzip. And that's because you see over here the files are actually in a .gz format, and luckily the function comes with this option that allows us to just extract it directly. It's a real pain to try to extract it yourself, so I'm thankful for this. Alright, and let's just take a look at our data. So let's notice the first thing about this. We have right there 2.26 million rows. So that's a lot. I actually ran into a whole lot of memory out of memory issues with. I guess Kaggle has a memory limit on the on how much memory you can have at a time. So I ended up after trying a few things, I figured the best thing to do is let's just cut the data in half and use half the data set. So that's what I'm going to do first thing. So we can use the sample function, data.sample, and we're going to sample half of the data. So fraction is 0.5. Axis 0 because we want to sample rows rather than columns. And we'll include a random state so we can reproduce 42. It doesn't matter what this is, I just choose 42. And then we're going to make data that. So now we should have half of... what happened? Didn't work? Oh. Wait, hold on. Let me copy in what I had before so I don't make a mistake here. Oh, what happened? It sampled the wrong way, didn't it? Yeah, look, we have 76 columns. So I actually have to sample 1, right? Okay, so let's restart this. I have to load data in again. Alright, give me 1 second. Alright, sorry about that. I'm not sure what was going on, but anyway, I'm using the same function. I specified axis 0 because I want to sample from the rows, and you can see we originally had 2.26 million rows. Now it's gone down to 1.13 million, and I'm going to set data equal to that. And this is what caused the problem last time. But I think we should be good, hopefully. Let's see. Yeah, okay, there we go. So we have the same number of columns, 151, and we have half as many rows. And this is just because we're going to constantly be running into out-of-memory issues if we keep proceeding with 2 million. And also note, this is sort of a beast of a data set. But what I mean by that is it's very messy. Very, very... it needs a lot of processing. So we also can't see all the rows, all the columns. So what I'm going to do is go into the console and type pandas.set option, max columns to none. So this way we can see all the columns. And I'm also going to set max rows to 200 just for the purposes of this notebook. Alright, so Now we can see all the columns, and you can see there are quite a few of them. A lot of them are just not, like, look how many null values are here, right? We're probably going to get rid of a lot of these features. But we're just going to do some preliminary sort of filtering exercises to try to figure out which of the features we really don't need and drop those. And the natural first thing to do with that would be, let's check how the missing values look. So missing values, we can use the isNA method of the data frame, and that will give us, it will return a true or false for each place, true being if there's a missing value there, false otherwise. With this, we can sum across the rows to get the number of missing values in each column. And you can see how long this is taking because it's a million rows. But you can see, okay, we have quite a few, especially down here. This is actually a million missing values, right? So what's probably better to do in this situation, instead of sum, let's take the mean. And if you consider, if you take the mean across a array of true and false, the trues will go to 1, the falses will go to 0, and that's the same as summing up the trues dividing by the total number. So that's essentially giving us the percentage of null values in each column. And so that should give us a percentage for each one. So this has 100% null values. Member ID is null all the way down. So we're obviously going to drop that one. But since this is all out of order, I'm just going to use the sort values method that comes with a Pandas series here. And that will just be, we'll be able to see which ones at the bottom, especially, how many of these are really bad. So member ID has 100% missing values, and then all of these have 90, 98%, 99% missing values. There's just no point in any of these columns, right? At least for our purposes. And I didn't mention before, but this is our target column. We're going to try to predict the grade of a loan based on other features. And this takes a value from A to G, A being the safest loan, G being the most risky. So we're going to define a threshold. It's sort of arbitrary, but what I noticed about these features is that there's a sharp jump between columns that have less than 38% missing values and columns that have more than 38%. So we could define this at anything like 0.5. What I mean by threshold is, like, if a column has more than a certain percentage of missing values, we're going to drop it. In this case, I think it makes sense to define that threshold around 0.3, because then we'll be left with this nice set of features, and we won't have to do any like extreme mean imputing or anything. Although 38% you could argue is still passable, I think for the purposes of this data set, it makes sense to cut it right there. So then that's what I'm going to do. I'm going to say, well, data.drop. Alright, before I actually enter that, let's take this thing, and we're going to want to get the names of the columns that have over 30% missing values. So if this is greater than 0.3, if we run a comparison on the series itself, it'll give us true and false depending on if that's true for each one. And if we take this thing and we index data at that thing, actually since we're indexing columns here, we should use .loc. Wait, are we? Yeah, no, yeah, we are. Okay. So all rows and only the columns that have this condition met. Alright? And that's going to look like, this should actually be a data frame, right? And this is now consists of 58 columns, which are these 58 at the bottom that have greater than 30% missing values, right? So from here down, this is a data frame of those columns. And now we're just going to drop those. So if I take that and I do columns, that'll give me the column names. And with that, I can then call data.drop on those column names, right? So these are all the column names for which the column has more than 30% missing values. And so I want to drop from the first axis, and data equals that. All right, and that should do away with a large number of the missing values we're dealing with. So let's take another look at data. And now we're dealing with 93 columns, and there's a huge percentage of the NA values are gone now. So that's really good. And another thing that's very good about having a lot of data is we can try dropping the rows that have remaining missing values. Because now that we're down to 93, we can hope that there's like a substantial number of examples in here that are completely filled out, that don't have any missing values. So if we do data.dropNA, which will drop either rows or columns that have NA values, depending on which axis we specify. We'll do axis 0 for rows. This will give us the new data frame with all the rows dropped that have missing values. And we want to see how many rows are we left with. And you can see we're left with 826,000 examples, which is more than enough data for our purposes. So we don't actually have to impute any values here. This is a really it's a really nice circumstance where we can just drop like I think it's like 400,000 examples, and end up with still more than enough data to do our predictions. So that's what I'm going to do. I'm going to drop those rows. So data equals that, and you can notice the indices have been messed up. So I'm going to do reset index, and I specify drop true here to avoid saving the old indices as a new column. So I'll run that, and when that's done, I'm going to get the total number of null values just so we can make sure, we can double check that there are no more remaining in the set. And so sum.sum means I'm summing across rows and columns, and we have 0. So we're completely done with missing values. Wasn't that nice? Okay. Now we'll move on to feature selection. So I'm going to look at the data. We're just going to keep looking at this thing, and we now have no missing values remaining. However, we have a whole lot of different data types and a whole lot of we're going to have to encode a lot of these data types. So we got to think, okay, whenever we are trying to deal with categorical variables or categorical columns, we have to figure out what kind of data is stored in each one. And I can do that with this. It's just one line of code that I love. I love this. It's a dictionary, and just by entering it, it will return the result. I could make this a function if I wanted to, but I'm just going to do it like this. It's going to map a column name to a list of the unique values of that column name. So I'm taking the data frame, the column of the data frame, and then getting the unique values of it, and then turning that into a list. And I'm matching a column name to each set of unique values, and that's for every column in data.columns. However, I only want the ones that have categorical contents. So if data.dtypes subcolumn equals object. So this will only return the unique values for the columns that satisfy this condition, which is the data type of the column is a string or an object. So we'll run that, and we should get this enormous list of all the unique values for every categorical variable. And there's a problem here. We have a bunch of really long features like with many unique values, and we just don't want them. So what I'm going to do up here is create this this variable called unneeded columns. That's just going to be a list. And over here, I'm going to do data.drop unneeded columns, axis 1. So you see what I'm doing now is when I get this list, this dictionary, I'm going to ignore columns that are in unneeded columns. And you can see ID is an example of a clearly unneeded column. This would be useful if we were trying to predict values for a specific person and we needed to retain the ID, but in our case we really don't care about it, and it's certainly not helping us predict the grade of a loan, so we're just going to remove it. So unneeded columns is ID, and now ID will no longer show up in our dictionary. Alright, so let's continue to filter these out, adding them to unneeded columns as we need. So term is useful, we'll keep that. Grade is obviously we're going to keep that, that's what we're trying to predict. Subgrade, this is not really good for us. Well, I guess you could say it is, but I feel like it is maybe a little too, I don't know, I feel like it's sort of like cheating, right? Because the subgrade has been like, it's defined after the grade is defined, right? Like in an actual setting, like where the grade is being given to a loan, the subgrade wouldn't be something that's taken into consideration when thinking of the grade. Subgrade would be like you give it a grade of A, and then you define it even further to be A2. So we're going to drop subgrade as well. So let's continue looking down. Employee title, is that what the emp? I don't know what emp is, but emp title. And we're just going to look how many different values are there, and there are a lot here. Right, this is a lot of different unique values. It seems very unfeasible to use these as one-hot columns. There's just too many, so we're going to drop that as well. So emp, what was it? Emp title. Okay. So let's just run it again now with these three gone. Continue looking. You can see it's getting more and more readable and manageable. And now we come to dates. And dates are actually useful information, right? Because I don't know, there may be some difference in time of year when it was issued. This is the issue date. Or even which year it was. So we're going to keep this data, and anytime we see dates, we're going to keep that. Loan status, also useful. Payment plan, also useful. URL, not useful. So we'll add URL here. Let's keep going. I'm going to scroll through this. There's a lot of them. Okay. Then we have purpose. That's useful, and there's definitely a manageable number of values here. Title. This also looks like it has way too many values. Yeah, so we're going to drop title as well. Okay. Keep going. Yeah, it looks like there's a new title for every single loan almost. Alright, then we have zip code. Zip code I'm also going to drop. Especially because what comes after it, which is the state. We'd have to add so many columns to deal with zip code or figure out some sort of alternate encoding scheme. Whereas we have this state one here, address state, which is it conveys a lot of the information that zip code would, in a much more like digestible way. So I'm dropping zip code, and then this is more dates, so I'm going to keep that. Earliest credit line. Keep scrolling. Let me just drag this down. Oh, we have one. Initial list status looks good. Last payment date, also going to keep that. Oh, and we have last credit pull date, also going to keep that. And then the rest of these look useful as well. So I think that's it. These are the ones we don't need. Now if we run this, with these removed, we should have all the good ones except with these big date columns. Dates aren't actually categorical variables, right? They're continuous in a sense. I mean, I guess they are categorical, but they're definitely ordinal, and we want to encode them as such. We don't want to, because you can say 2018 is definitely greater than 1957, so they take a certain order, and you can also say March is less than December. Sort of arbitrary how you define months, but we're going to use ordinal encoding for those two. So I think we should deal with the date columns next, because they're taking up so much room in this, and it's making it difficult to like get to these guys. Let's just tackle them first. So now that we have this, we're actually going to drop the unneeded columns. So I didn't drop them yet. I was just showing this dictionary. Data.drop unneeded columns axis 1 and data equals. Okay. And let's deal with some date columns. So dealing with date features, let's say. Okay, so which are our date features? I think we have 4 of them from what I saw. Issue date. So let me just make this date columns is going to be a list of all of these. We start with issue_d. Then we have, here, I'll just scroll through this. This one here, earliest credit line. Keep going. And here's one, last payment date. And I think there's one more down here, right here. Last credit pull date. Alright, and that's it. Okay, so now with these date columns, what are we going to do? Let's notice something. Let's work on one of them. Let's just say, okay, data sub issued_d. So this is the list of dates in month, year format with a hyphen in the middle. So notice that they all actually take the same shape, which is 3 characters, a hyphen, and then 4 characters, where the first 3 are the month and the last 4 are the date. Are the year. So if we did, let's just take one example. We'll take the 0th index, right? So 0 issue D. This would just be February 2015. Now if we index this from 0 to 3, we can actually just get the month. Similarly, if we index it from -4 until the end of the string, we can get the year, right? So we can use these to construct new columns, new features. So this is good. Let's make a loop then. Let's do this for all of them, right? So for column in date columns, so for each date column, and luckily all of them take on the same form, so we can do this, data sub column. So this would reference the actual date column, but I want to make a new one, which will append _month to the end. And so this would be issue D _month, right? And that would give us a new column, which we can set to be data sub column, which is the original one, dot apply lambda. So this is a lambda function that takes in some x, which would be a single one of these values, and it's going to spit back that same x, but only from 0 to 3. So it's going to map each of these to be just the first 3 characters, and then it's going to store that in the new column, which is issue D _month, or one of the other date columns. And then we're going to do exactly the same thing, but for year. So this would be _year, and this will map from nothing until, sorry, no, -4 until the end of the string. And if we run that, and we check data, and we just go to the end, you can see we now have these wonderful new columns. There should be, what, 8 of them? 2 for each original date column. 1, 2, 1, 2, 1, 2, 1, 2. Fantastic. And now we're ready to go, right? Now we can encode these months to be numbers, and we'll have fully numeric data concerning the dates. So we're going to drop the original date column. So data.drop date columns, axis 1, and data equals that. All right, and great. Your notebook tried to allocate more memory than is available. It has restarted. So let me pause this. I'll come right back. I'm just going to restart the program because it just takes a while to load in the data. All right, so we're back, and we fixed the memory issue. I think it just from running generating the data over time is just building up stuff in the background. I hope we don't run into it again, but let's see. So now I'll take a look at the data again after we've dropped that. And okay, so we don't have the original date columns anymore. Now we have these nicely encoded ones. But before I get into encoding all the features, I'm just going to get rid of, I'm going to encode the month columns separately from the others. So to do that, let's say we still have this variable called date columns, right, which is all these. And let's say for each column in date columns, well, let's reference the column underscore, plus underscore month. So this will get all of these. This one, this one, this one, and this one. Right. So we're going to take those, and we're going to apply a Lambda function to them, which takes in some x, which would be one of these. And we want it to give back a number that refers to each month. So for that, we're going to make a list called month ordering, and that's going to be just a list of months from January to December in order. And just to save on time, I'll paste this in because I have it written down. So it's just January, February, March, April, May, June, July, August, September, October, November, December. This would be 0. This would be 11. Right? So all we have to do is now convert a value, we'll index it in this list, and get back the corresponding value. So that would be 5. Alright, 0, 1, 2, 3, 4, 5. So all we have to do is take in some x, which is one of these, and return month ordering dot index at x. So it'll take this in, feed it through the month ordering, get back the number, and then set that equal. And we're going to store that in the same column. Alright, run this. Month order, oh, I didn't run this first. Okay. And then we check the data after that is done. We now should see that all the months have been encoded as their proper numerical equivalents. Very nice. Alright, so now, okay, before we proceed, before we do the encoding, let's just try to, this is probably unnecessary. I assume these are numerical values, right? The months definitely are, but I think the years are not. The years are probably still strings because we sliced the string, right? So what I'm going to do is just, for every column in data.columns, we're just going to try to convert it to a float as type numpy.float. Okay, and upon running into an error, we'll just do nothing. Pass. Alright, and so now all these should be float values. Now we're going to check that dictionary again. So we had it up here. Where is it? This one? So this, except I'm not going to drop unneeded columns anymore. This is just all columns. So again, we're taking a column name, one of these, and we're going to map the column name to a list of the unique values in that column, but only if that particular column is an object data type. So we're going to check that, and now all our dates should be gone, And sure enough, we have a nice workable set of features. So what we're going to do now is take each one of these and classify them as binary, ordinal, or nominal. And so a binary feature would be one that takes on only two values. For example, this is binary, 60 months or 36 months. This is binary, n or y. And ordinal features are going to be ones that take on more than two values, but in a particular order. So this is an ordinal feature, right? Because less than 1 year is less than 6 years, which is less than 8 years, etc. And the last type would be nominal features, which are features that take on more than two values but do not have any sort of order. So this is a nominal feature, right? There's no way to compare rent to mortgage to other. So I think most of these are probably nominal. So what I'll do is just make these three. Here, why don't I do this? Encoding. Alright, I'm going to make three lists. One will be binary features. One will be ordinal features. And one will be nominal features. And I'm also going to include the target. Whoops. The target, this is the target column, is going to be grade, right? The one we're trying to predict. Grade. And not a list, just a string, so that we could reference it later without typing grade. We didn't need to do this, but it's nice to see. Alright, so now we're going to go through and start throwing them in the corresponding buckets. So term, this is binary, right, because it takes on two values. So I'm going to put it right in there. Next we have grade, which is not a feature, that's what we're trying to predict. Emp length, maybe employment length, is not an ordinal feature because it takes on an order. So we're going to throw it in here. Home ownership, this is nominal, right, because there's no order between those values. So throw it in here. Verification status, this is also nominal, since there's more than two values and they don't take an order. I mean, you could argue that there's an order there, but I think we're going to keep it as nominal. Loan status, this is definitely nominal. I mean, if you could maybe find a way to order that too, but it would be difficult. It would be hard to say that current, is that greater than fully paid? Is that greater than late? It's sort of arbitrary. So we'll keep it as one hot or nominal. This payment plan is going to be binary because there's only two values. Then we have purpose. This is nominal. Then we have address state. This is also nominal. Then we have initial list status. This is binary. And I think the rest of these are also binary. So application type, hardship flag, disbursement method, debt settlement flag, and that's it. Okay, so now we have sorted all of our features into these three categories, and we will encode them corresponding to which category they're in. So what I'm going to do is I'm going to make three functions. One will be for binary encoding. You can take in some data frame and a column and a positive value, and I'll explain that in just a second. Then we have ordinal encoding, which will take in a data frame, a column, and an ordering. This is very similar to what we did with the months before. And then one hot encoding for nominal features. It will take in a data frame and a column. And so before I write these, I have to specify a few things for binary and ordinal. So I'll start with ordinal because we've already seen it. We need to give it an ordering. So just like we had the month ordering before, right? Where is it? Right here, we ordered the months so that we could index the list to get the proper numbers, right? So February went to 2, right? So we need to give it another ordering, this time for emp length. So what I'm going to do is just copy that list, and right here I'm going to write emp ordering, and it'll look like this. And I'll just clean this up real quick, make it nice, and bring this over one. Alright, and now let's rearrange it. So there's only a few changes here. Oh, actually, hold on. Let's do this. Data sub emp length dot unique. So this is like what we had earlier, but I'm also going to sort it just to make our lives a little easier. That should be parentheses. Oh no. Alright, we'll use this one. So this is already sort of sorted. Okay. So I can delete that. Let's see what we have to do. Put 10 years at the end. Put less than 1 year at the beginning. I think that's it. Less than 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 plus. Fantastic. So this is the proper ordering of the emp length feature. Now for binary features, we want some control. I mean, it really doesn't matter, but it's nice to know which value we want encoded as a 1 and which value we want encoded as a 0. So what I like to do is make this list binary positives. This will be a list that will each element in the list will correspond to one of these different columns, and it will be the value of that column that we want encoded as a 1. So for example, for term, up here 60 months and 36 months. It's arbitrary which one we pick, but let's say we pick 60 months as our positive value. We'll just put that in. Whoops. And so this just matches up, right? So the next one will be for payment plan, which is N or Y. I think we'll use Y for positive. That makes sense, right? So we just put that there, and now that matches up to payment plan. Then we need one for each of these. So the next one's right here, actually. W or F for initial list status. We can just pick W. Application type, let's say individual is positive. And then we have hardship flag, we'll say Y, capital. Then disbursement method, this would be cash or direct pay, we'll do cash. Debt settlement flag, N or Y, that will be Y. Okay. So now we have all the positive values, each one matches to a different, right, it maps, right? Each one is for a different feature, and then we have an ordering for the only ordinal feature. If we had other ordinal features, we would have to make other orderings as well. But this is really good. Is now we can write these functions and just work on them as we need to. So usually when I write these functions, I make an effort to make copies of the data frame, so as not to modify the data frame in place. So that tends to be bad practice, trying to avoid side effects and such. But because we're running into memory issues, I'm just going to modify them in place using direct column indexing for pandas. So we have some data frame we're passing in. For binary encode, I'm just going to actually modify the data frame. This is a pass by reference, so it's actually going to change the column. And so we're going to apply a lambda function. It's a very simple one. Just takes in an x, returns a 1 if x is the positive value. And otherwise, we'll just return a 0. So this is essentially just binary encoding, right? It'll be 1 if it's the one we specified, otherwise a 0. And that's it. We don't have to return anything because it's doing it in place here. And down here, we're going to do a similar thing, but instead of this lambda function, we're going to apply the one we used earlier, which is we're going to take some ordering that we specify, and we're going to index it at x. So that'll do the same thing that we did with the months before. Then lastly, a one-hot encode. This one's a little more. We're going to make a dummies matrix, or a dummies data frame, which will be pd.getDummies. This will just be the one-hot columns for the column we'd like to encode. And we're going to get it for that particular column. Then we will make this new data frame, dfNew, which will be a concatenation of the old data frame and the dummies. And the reason I am now going to return data frame for this function is because we can't assignment to the df will create the local copy. We'll create a local copy within the function. That actually won't affect it in place. Whereas assignment to a column index of a data frame will affect it in place. So I think Pandas encourages you not to use this kind of setting in a column because it does it directly in place. Whereas, like if we tried to do df equals, this would create a new df that would not affect the original df. Alright, it's just a side note. We're going to make dfNew is pandas.concat the original df and the dummies along the first axis. So side by side, that means. And then we're going to drop the original column from the first axis. Sorry, it's not the first axis, it's axis 1, which is the column axis. And then we'll just return dfNew. So this one actually returns a data frame. Alright, now we have our functions. So yeah, I'll just put a little comment here. Encoding functions. Alright, and we're going to actually perform the encoding now. Which, so we'll do it in 3 steps. First we'll do binary. So notice that I have this thing which is binary features, the names of the columns, and binary positives, the positive values for each column. Python has this wonderful function, built-in function called zip, that can take two lists, so binary features, and binary, positives. And it'll zip them together. And so if I show that as a list so we can see what it's doing, it'll go element-wise down the lists and group the elements into tuples, like 2 at a time. So this one from binary features, one from binary positives, that's one tuple. Then one from binary features, one from binary positives, that's another tuple, and so on. So very useful, because now we can run a for loop that can take one from each. So what I mean is for feature and positive value in this zip. So now we can get two iterators you could think of as we go through this zip. We will binary encode, and we just run this in place. We don't assign it to anything. The data frame, the feature, and then we pass in the positive value. And that should do what we want. Alright, then we'll just run in place ordinal encode data emp length, because this is the only one, emp length, right? And we pass in emp ordering as well. Alright, and lastly we do the one-hot features. So for feature in nominal features, right, so let me close this out. Right here, these ones, for each one, we're going to set the data equal to one-hot encode data and feature. So in this case, I'm actually setting the data frame because I'm adding new columns to it. I'm not just modifying a single column like I'm doing here with these ones. So run that, and when that is done, we can check if we get the D types. We want to check if any of the data types of the columns are object, and then we want to sum up all of those. So we go see how many left do we have that are string values, and we only have one, and that one happens to be our target. Our target, if we remember, data sub target, that's the same as grade, is A through G values. Dot unique. Actually, I'll do dot value counts. You can see we have the most in C, the least in G. This is what we're trying to predict, right? Which category does it fall into? And we're just going to encode it with label encoder from sklearn because it does the job very well. So we will encoding label column, and we'll make a label encoder object. That is that's from sklearn right there. And all we have to do is data sub target, so that's data sub grade, equals label encoder dot fit transform data sub target. So all that will do is it will map each one of these to a value from 0 to 6. So there's 7 total. And let's say we want to see what it mapped it to. We can actually check that, make a variable called target mappings. Well, it will be a dictionary that maps an index to a label. For every index label pair, and enumerate the label encoder dot classes attribute. So this is a list of the classes it encoded in the order that it did it. So by enumerating it, we can get the actual value that it mapped to. And we can see what that looks like here, target mappings. And you can see 0 went to A, 1 went to B, rather A went to 0, B went to 1, C went to 2. It did it in alphabetical order. So very nice. Did exactly as we wanted. And now we can move on. So let's note that now our data should be fully numeric. Right? If I run this, we'd get 0. There's no more text in our data. So let's look at it. It's a fully numeric data set. And I realize I should actually, because when I reset the runtime, I had to, this got reset. So max columns is none. Now we can see all the columns. And we have 167 columns now, but they're all numeric. So that's very nice. One of them is not a feature. One of them is the one we're trying to predict. Where is it? Should be somewhere near the beginning, right here, grade. So this one, we're going to separate from the rest. And so I'm going to make this section called splitting and scaling. We're getting ready to train, almost. So Y is going to be our target column, which is grade. So that's data sub grade. And then X is going to be everything except grade. So we're dropping it from the column axis. Now we're going to make a scalar, which will be a standard scalar from sklearn, which will give each column mean 0 and variance 1. So that they all the columns take on a similar scale of values. Alright, and then I'm going to fit the scalar to X. So scalar.fit, and I'm going to transform X as well. So fit transform X. So this will just, it'll do exactly what I said. Convert each column to have mean 0 and variance 1. And yeah, this happened last time as well. I'll just restart the runtime. Give me 1 second. Alright, we're back. And I'm going to, so the scaling completed. And now I'm going to split the data into train and test sets. So xtrain, xtest, ytrain, ytest equals, we're using the train test split function from sklearn, passing in x, y, a train size of 70%, and we're going to include a random state as well, which will, let's make it 42 again. So run that, and we'll start training. So, well, it's modeling and training, I should say. Alright, so we're going to make a TensorFlow neural network. A pretty standard architecture. We're not doing anything fancy because it's all text data. I mean, tabular data, I should say. tf.keras.input. So this is going to be the size of our input vector which we can check. Oh, this should be inputs actually. X.shape. So we have 826,000 examples and 166 columns. So that's going to be the length of our vector. Then we will have a hidden layer, dense layer with 64 activations, with a activation function of ReLU, passing in inputs. We'll do the same thing for the next one, passing in X, and for outputs we will do another dense layer with the number of activations here should be the number of output classes that we have, which would be 7, right? One for each of these, 0 through 6, so 7, and that gets an activation of softmax so that we get a probability estimate for each class. And then we get X, we pass X in there, and then we create the model, which is tf.keras.model, passing in inputs and outputs. And then we'll compile the model. So we'll use standard optimizer here, which is atom, and loss function, sparse categorical cross entropy. And for metrics, I think accuracy, multi-class accuracy is probably a decent one to use here. Yeah, the classes aren't too skewed, especially since we have a nice variety of them. But if you wanted to use other metrics, we could. Let's just keep it as accuracy for now. So batch size is, let's make 32. Let's train for 20 epochs. And let's store our model's fit history in history, a variable. So that'll be model.fit. We're going to fit it on xtrain, ytrain. And we're going to give it a validation split of 20%. Then we'll pass in the batch size and epochs. And we're going to include a callback function, which would just be so callbacks equals tf.keras.callbacks.reduce learning rate on plateau. This will just help our model converge. And because this has been a long video, a lot of it has been on data cleaning, I'm not going to go so in depth about the model optimization here. Alright, and I think we can start trading it. See, that works. And we have to start the notebook again. Okay, so 1 second, guys. Alright, so we're back and the model has begun training. You see already we're getting a very promising starting point. I'm training for 20 epochs here, and I think it should probably be enough to converge based on what I was doing earlier. I think we could let it go for longer, but for our purposes, I'm just going to leave it like this because we're not, I mean, you'll see, we'll get pretty good results, I think. Let's start plotting it. We'll plot a loss graph to see that how our loss and validation loss is going as we train. So I'll use matplotlib, set up a figure, give it a fig size of 14 by 10, and we're going to define the x-axis, which will be the range of the number of epochs. And so epochs is 20, so this will be 0 through 19. So we'll just plot the number of epochs on the x-axis, and for the y, we'll use train loss, which will be the array of loss values for each epoch, which we get from history.history subloss. Then we'll do the same thing for validation loss, but we'll index at val loss. We'll call this one val loss. And then we can plot it. So right now this is looking very promising, right? Nice. Epochs range on the x, train loss on the y, and we'll give it a label, training loss. Then I will do the same thing for validation. And here, make this val. Alright, then we'll set up the axis labels. For the x, we'll have epoch. For the y, we'll have loss. We'll give it a title as well. could say loss over time, and we'll turn on the legend, and we'll show. Now I'll just pause this here because I don't want to make you wait to train. I'll come back when it's done. Alright, training is done, and you can see the last iteration we had 98% accuracy in the validation set. So let's check the results, and you can see it's converged very well. I mean, this isn't showing us too much because we didn't train for probably as many epochs as we should have, but because this is such a long video and we're almost at an hour here, I've just spent so much on the data cleaning. I'm not going to go so in depth on the model optimization right now. So this is perfectly good for our purposes. We're going to evaluate it on the test set, and then we'll be done. So x test, y test, and we get a final accuracy on fully unseen data coming out to be 98.23%. So very good, right? Really good. And as the saying goes, if you have enough data, anything is possible. So, I mean, we really did have a huge amount of data here too. So we also had a really nice variety of features. Even though we stripped away so much of the original data set, we started with 2.2 million rows and 151 columns, and we ended with 826,000 rows and 91 columns. That's not counting the one-hot columns that we created from them. Even though we stripped it down to that, we were still able to get very high accuracy, very nice performance on this model. So I know this was a very long video, but thank you so much for watching. If you enjoyed, make sure to subscribe and hit the bell for more content. And leave any comments in the section below if you have any suggestions for the channel. I'll see you guys tomorrow. Have a fantastic day.